Yeah, red block trees. Today we'll continue, from the balanced binary search trees. Uh, red black trees is another kind of balanced binary search tree. When you say it's a binary search tree, so all the properties of binary search tree are quite applicable here. As we know that binary search tree, wherein you have a special node called root, and left subtree will have the lesser values than the root, and right subtree values all are greater than the root. So this kind of property is going to be recurrently applied on every particular node. This is exactly what we have discussed as part of binary search tree, right? Now coming to red black trees here. Uh, Now here, this is another kind of balanced binary search tree, very similar to that of your AVLs, play, and B trees kind of thing, right? So kind of operation that we can perform here are again same insertion, deletion, and such. And if you look at the time complexity is not more than 2 logarithmic n, which is equivalent to height of the same, rather, right? Now, if you look at the properties, before going for the operation, we'll just look at some of the properties, which is as part of definition here mentioned. Every node is red or black. There are two colors here mentioned, right? Every node could be either colored in red or the other color could be the black, rather, right? And second property that we are saying is the root is black here, right? Root should be black here, and every leaf node, right? Leaf nodes always all on the last level, right? So they're all should be nil. Every leaf is a nil and is a black node, rather, right? And if a node is red, in between, if you have any node is red, then both its children are black. This is a condition. If a node is red, then both its children are black. For each node, all paths from the node to the dissident leaves contain the same number of black node. It means from for each node, if you probably take any node, the paths that are taken until you reach the leaf nodes, rather, right? So the paths across the paths, if you look at in its dissident leaves, the number of black nodes should be same from any node, right? So this is another property, this is another important property. So these are the five properties with which the red black trees are going to be constructed here. The first one, as I said, is every node either red or black, the root is black, every leaf is nil and black, and if there is a node red in color, then both of its children should be black. And for each node, if you probably see the paths from the nodes, if you look at the paths that are going to be let out from any node, uh, across that path, if you look at the till the dissident leaves, right? If you look at the number of black nodes should be the same. Okay, so this is another property, fine. So you can see an example of the same. You can mention it's mentioned here in this particular screen, where you can see this is red, this is black color, this is red, right? So you can see here, as we said, all the leaf nodes are nil and black. So these are all the leaf nodes, nil and black, and root should be black, we said. And if any node red in color, this is red in color, this is red, and this is black, right? So if any node red in color, then both of its children must be black. You can see this is it. So one left child and this is another right child. So both of its children must be black. And another condition here, another property that we said, that from any node, the dissident leaves, if you probably see, the number of black nodes should be same, right? If I take this particular node from here, how many paths that I probably come across with until I reach the leaf node? This is one path, right? And this is another path, and this is another path, and this is another path. So just look at across the path, how many black nodes are there, right? You can see across this path, okay. If you include the leaf node also, it will be 3 here. If you see this path is again 3, you can see, yes or no? Can you probably see if I add this nil also, 3, right? And this is another path. You can see this is also 3. This is another path, right? is also 3. Yes or no? This is another path. Yes sir, is also 3. Yes sir, how many paths? This is one path, this is another path, this is another path. So across all the paths you can see, right? Across all the path, the dissident leaves are, when you identify, they are, you know, having equal number of black nodes. Yes or no? Across all the paths, the dissident leaves, if you probably look at, having the equal number of black nodes. Yes or no? This is another fifth important property. So now, what are the fields that you find? Um, you have left child, you have a right child, you have a parent, you have a color, you have a key, right? So in addition to key, left right, you have another property or another field. The other way around, I can say, in addition to the fields that you have in binary search tree, is the color. Okay. So a red block tree with n internode has height at most 2 logarithmic of n plus 1. Okay. So the operations that you can perform are, searching, finding the minimum, maximum, successor, and predecessor. Of course, insert and delete are the major operations that you can perform. As you must be knowing about left rotation and right rotation, right? When you apply the left rotation, the tree which you get, on which if you apply the right rotation, you will get the tree back, right? The same tree back, right? Because these two operations, left and right rotation, are symmetric in nature. Yes or no? They are symmetric in nature. So the here you can see, operation is mentioned here. Left rotation. How do you perform a left rotation if you have a tree like this? Okay, you're performing a left rotation. uh, when you perform a left rotation here, yes or no? So what happens? This y will occupy here, but then this beta goes to the right of x and x will come to the left of y, and y will occupy the root position. That is what exactly here mentioned. You can see y is right of x, right? Y is nothing but right of x, and right of x, in right of x, what do you take? Left of y. Left of y is beta, right? So that left of y you will assign it to right of x. So then beta goes to the right of x. Then if left of y is not equal to null, if left of here, if left of y is not equal to null, p of left of y equal to x, and p of y equal to p of x. Okay, so while attaching to their parent, rather, fine. So do that. And then if p of x equal to null, if parent of x is nil, then y becomes the root. Yes or no? If there is no parent of x, then y becomes the root. That is what exactly you said. Otherwise, what do? You will attach this y to the parent of x by identifying where does it go. Fine. If left of p of x equal to x, if let us say x could have been at the left of its parent, right? Then this y go to the left of its parent. If it is right of its parent, then y goes to the right of its parent. That is what exactly you are saying here, right? If left of p of x equal to x, left of p of x equal to y, else right of p of x equal to y. Then you make the left of y equal to x, right? So x here, left of y, in left of y, x will be attached, you can see here. And p of x, the parent of x becomes who? Y will be the parent of x. This is what exactly. So this is the left rotation in complete operations mentioned. Fine, you can see here. So again on this tree, the transition after took place when I perform a left rotation on the particular tree. I again apply a right rotation. I get the same as what I had before I apply left rotation, because they are symmetric in nature. So you can see here, this is a left right rotation algorithm. So when you apply the right rotation on this particular tree, fine, that is your x, right? Left of x is left of y, yes or no? And left of y equal to right of x. In left of y, what do you have? you will take this beta and take get it attached to the left of eye. See, left of eye. When you apply a right rotation on this, what happens? This beta goes to the left of y. That is what exactly you are saying here. If right of x is not equal to null, if right of x is not equal to null, then parent of right of x equal to y. So right of parent of right of x will become what? Y will be the right. Okay. Then p of x equal to p of y. You say parent of x is who? Parent of y. If p of y equal to null, if you do not have parent of y, right, then root equal to x becomes root. Otherwise you will be attaching this x to the parent of y. If parent is at the left, then x goes to the left, or else if it is at the right, it goes to the right. Okay, this is left and this is right. Okay, anyway, so when you perform this operation, you get back the tree when you have applied left on the same ladder, right? So I hope this is clear. This left to right rotations are I have explained you before also, rather, right? So you can probably take one tree here. You have a tree like this. In this, let us say you want to apply a left rotation on, you know, x. So when you apply a left rotation on this, what happens? This 18 will occupy 11 position, and this 14 will go to the right of 11, and 11 comes to the left of 18. You can see left of 18 will be 11, right? And this 14, which is the left parent of left child of 18, goes to the right of 11. You can see 14 is attached to the right of 11, right? So this rotation anyway you are clear with. In ABL tree we have discussed about it. Now, coming to insert algorithm of red black tree, this insert algorithm is very similar to that of a binary search tree only. What is that you are doing here is, first you're creating a new node, right? Initially, the root is null anyway, fine. So if x is not null, then you probably continue here. Otherwise, your x is root itself, right? If the node is the first node, then probably that becomes the root. Then what do you do if the node to be inserted is not the first node? Then you will have to search for the parent, right? You will have to search for the parent. Let us say you want to insert a new node here. You have a 50, 30, let us say 40, this is 35. 35 is inserted now, let us say. 35 has to be inserted. So how do you insert? You will start from root first, okay? You start from root and then search for the position, right? Since 35 is less, so you move here. So that exactly here, this particular logic is finding you the parent. This particular logic is finding you the parent of this particular node, the node which you want to insert. Node you want to insert is nothing but z here, right? This is a z. Fine. So how do you find? You can see here you start with y. Y you have considered x is your root initially. X you start with root. So then you take the x in y. You take the same x in y, and you compare your z key value, that is 35, with x. If it is less, then you are moving x to the left of x, right? It is anyway 35 is less, so you move x to the left of x. So x is here, but y is here only, right? And again you come back, and then this is in a do while loop, right? So y will be taken here on x again. Y equal to x, when you say y comes here, not here, so y is here. Again you are comparing your key. Your key is 35. 35 is less than 30 is false, so you go to the else part. In else part, what you are saying, x gets right of x, so x will be from here to here, rather, right? It comes here. Then again you go back and make your x with y, right? Okay. Again this is going to be repeated how long? Until x is null, right? Until x is null. Now you can see 40 is compared, your key is compared with 40 keys, 35, 35 is less than 40, 40 is false. So you go to the else part, and when you go to the left of the same, it will be null. Initially, it is null, right? This is null, right? Initially, so x becomes null, so you come out of the loop. So y is your parent. You can see y x is null, but y is here itself at 40. So y is your parent. So that's how exactly p of z. This is your z, and this p of z is nothing but your y. I am saying. Now this z has to be attached to its parent, that is y. So how do you attach? If it is less than the parent, you attach to the left. Otherwise, you attach to the right. So you can see here key of z with key of y you're comparing. If it is less, then z is going to be attached to the left of its parent. Otherwise, it will be attached to the right of its parent. So this is simple binary search tree insertion procedure itself, right? So till here it is simple binary. So 35 is inserted to the left. That is done. Then left of z, what do? You make it as null. This is your z, and you make this left as null, and the right also you have to make it as null because you don't have further right, and you make this color as red initially. What it will be in color? It will be in the red color. The node which you have just now inserted always always colored as red. Then another algorithm is where you have to do the coloring adjustment, is what called the insert fix up. So now you go to the insert fix up, you'll call the, so what are the situations with which the properties are going to be violated are mentioned here. Each node block are red as per the properties, right? Each leaf is black sentinel. Same number of blocks should hold from any node to its dissident leaves, right? And root should be black. And if there is a child red in color, then both of its child must be black. So these are the properties. Now let us go to the insert fix up after you insert the node. So here you can see insert is very similar to the of binary search tree. After you insert the node, what you do, you are coloring it to red. Here you can see, right? You are coloring it to red, and then calling the insert fix up to adjust the colors, right? So the checking these five properties, taking into consideration, if anything gets violated, we will be identifying these three possible cases: case one, case two, case three. So I'm going to discuss these three cases. When you encounter with any of these three cases, you need to apply the appropriate mechanism here that is mentioned in this algorithm, and then you will bring back that particular tree into the red black tree by satisfying its properties, rather, right? So when you have made that particular node color red, let us say, okay, this is your z, right? So you have inserted, let us say, 4 in the existing tree. Now, after you have inserted, you make that node color as red. But then its parent color was also red. Fine. See, before this node was inserted, you can see the tree was in AVL because root must be blocked. You can see, and if there is any node red in color, then both of its, what do you call, child should be black. So it's all satisfying. But then when you are inserting now here Z, what is happening? You got red, right? See, Z is red and its parent is red. When you find this, this is a violation, right? Parent, if it is red, right, red is a violation. So under which particular case that it is coming is, like you can see here, this is the first case I'm considering, right? So in that case, what I do here is I apply the required mechanism that is mentioned here. This is case one. So see what is happening when color of y. Y is what? Y is the uncle sibling, right? Your Z, you're checking color of parent of Z is red, right? Until color of parent of Z is red, you have to repeat this. If parent of Z is left of parent of Z, you can see here the you can see parent of Z is at the left of its parent of Z, right? You can see its parent is at the left of its grandparent, yes or no? Its parent is at the left of its grandparent, okay? Similarly, when the you can find, you have the else part here, right? Same as the then class. So if the parent of z is at the right of p of z, the same case, three cases will be repeated under else part as well, right? We are seeing one part of the same. The similar symmetric part you will find when your parent, when the parent of z, when the parent of z, that is 5 rather, right, is at the right of its grandparent, right of its parent, the other parent, right? Then again you will find three cases. But anyway, just looking at the left side scenario with three cases, if you probably look at here, what is happening, you can see z is the node which is just now added, with which the property violation took place because its parent also read, and its parent is at the left of its grandparent. And we will identify the uncle sibling. This is the uncle sibling, right? As parent, z's parent is 5, and his grandparent is 7, right? Yes or no? And grandparent, right, you have 8. 8 is the sibling of 5. It means sibling of the parent of z, that becomes the uncle sibling of z. Okay, so I am taking all these three into consideration. Y is the uncle sibling of z, 5 is the parent, 7 is the grandparent, right? In the algorithm also, that is what exactly here mentioned. You can see we have taken y is the right of parent of z, right? Right side of grandparent is nothing but the uncle sibling, right, of z, right? Now we are checking that color here. If that color is red, yes or no, that color is red here, yes. So in that case, what do you do? Color of parent of z, you make it as black, and color of y also make it as black, and make the grandparent as red, and then advance this z to the grandparent, right? This is what exactly the case one. Case one is a very simple one. What is that we are trying to do here is, we are fetching this uncle sibling. See, the parent color was already red, that is what the violation. Then we were identifying the uncle color. Uncle color is also red. Fine. Then what is that we are applying here is nothing but we are making this as black, it is black, and we are making this as black, and making the grandparent as red, right? You can see making grandparent z, and advancing z to the grandparent. Z is here. Yes or no? Now z is here. Advancing z to the grandparent. That is what exactly you have done in the case one, right? This is your case one. So now when z is moved to the grandparent, you have encountered here with the second case. That is, your z is at the right of its parent, right of its parent. Yes or no? See, Z is at the right of its parent, and its parent is again red. Red means again violation. You can see Z is at now 7. See, after case 1 solution is applied, 7 has become red, and because of 7 is red, its parent is also red. Red means again violation, right? You cannot have red and its parent is red. Both cannot be, it's a violation. That is what exactly here also, right? Then only we have gone for the case 1 solution, and after case 1 solution applied, we got again red. So now Z is at the right of its parent. Yes or no? Z is at the right of its parent. So this comes under, you can see the second case, right? If Z is at the right of the uh, right of its parent, then what is that you're going to do? You make parent of z as z, and then you apply a left rotation on z. Okay, and then make the parent color of z as black and grandparent of the same as red. Again, you apply a right rotation. That is case 3. So you can see first we look at the case 2. In case 2, to solve, you can see here what is that we are trying to do here. We are applying a left rotation. When you apply left rotation, 7 comes here at the 2, and 2 goes to the left of 7, and right, left of 5, 7. Left of 7 will go to the right of 7. Right of 2, right? left of 7, that is 5, will go to the right of 2. You can see here this 5 has gone to the right of 2, and 2 will come to the left of 7. 2 will come to the left of 7, and 7 will occupy the uh, you know 2 position, its parent position. So after you apply a right rotation, you got this tree like this. But then again, it is red. Z is where is Z now? Z is here, and its parent is again red. So this is coming under case 3. That is, you can see when I am saying it is case 3, when the uh, Z, when the node is at the left of its parent, when the node is at the right of its parent, that is case 2, where you are applying a simple left rotation. But when the node is at the left of its parent, then it is coming as the case 3, right? You can see here, when the node is at the in the else part, that is in the else part we are seeing, right? So we have to apply the right rotation. In this case, what is that you're going to do? You will be applying a right rotation here, right? So when you apply a right rotation, what happens? uh, you can see here, you'll be applying a right rotation on whom exactly? You can just look at here. You'll be applying the right rotation on its grandparent, not its parent, but on the grandparent. You can see, making the grandparent color as red, making the parent color as black, and then applying a right rotation on the grandparent. So it means making its parent is 7. 7 color you are making as black, right? This is going to be made as black. And grandparent is 11. You are making it as red. This is going to be red. And you are applying a right rotation on grandparent, not on the parent. Okay, on the grandparent. When you are applying a right rotation on the grandparent, what is happening here? You can see here the 7 will occupy the root position, and the right of 7 will go to the left of 11, and 11 comes to the left of 7. That's how exactly. Now after doing this, you get the tree like this, and the colors also adjusted. You can see the root should be black, and if any node internal is red, both of its child is black. You can see both of its child is black. Fine. So from any node, the dissident blocks should be same. The dissident leaf should have the same number of block nodes. This is one path. This is another path. You can see this only one black node. This is one black node. Similarly, here you can see one black node, one black node. This part satisfying the properties, right? So these are the three cases you encounter with. First case is, first thing, when you insert is very similar to that of your binary search tree, right? Once after you finish insertion, you will give the color of the newly inserted node as red. Then you will be here identifying the three cases when it gets violated. When do you think that the property is violated? When the node and its parent node both are having the red in color. So after you insert, Z is red and this parent is red. So this is the first case. Why I am saying it is the first case? When you find its uncle sibling is red, okay, its parent is red anyway, because of which it is violated, and you are identifying its uncle sibling color. Uncle sibling color is red. Then what do? You make the parent and uncle sibling color as black, and you convert the grandparent color to red, and you advance Z to grandparent. That is what the case 1 solution. Case 1. In case 1, when do you find basically node and its parent in red? Uncle sibling color is red. Then what is the solution? Make parent and uncle as black. Yes or no? And grandparent GP is red. Got it? And make GP grandparent as red. Then advance Z to grandparent. So this is case one solution. So you see what is that exactly? That is what exactly I have done or not? See, uncle sibling is red, so parent and grandparent as made as black, and its grandparent made as red, and you have advanced Z to here grandparent. Then under case two means when you find. See, I am considering all these cases when the node and its parent both are red in color, then only I say they are cases, right? After I advance Z to its grandparent, you can see the parent of Z is red in color. So it's a violation, red. So when it is a violation, and then you are identifying this as a case 2 because Z is connected to the right of its grandparent. Sorry, right of its parent. Sorry, Z is connected to right of its parent. Then you apply a left rotation on simple left rotation on its parent. That's it. When you apply a left rotation on parent, what do you get here? 7 will occupy here. You can see, and 2 will go to the left of 7, and 5 will be attached to the right of 2. That is what exactly it is. Then again, after doing this, you can find your Z is at 2 and its parent is again red. Now, this particular case is something like case 3, right? So, in case 3, you can see the node is connected to the left of its parent. When it is connected to the left of its parent, what is that you're going to do? You will be applying a right rotation on its grandparent. Okay, you're applying a right rotation on grandparent and making some of the changes, right? Under case 3, that is node is at left of parent. Then what do you do? Apply right rotation on grandparent. Case 2 means node is this one. Node is at the right of parent. Then apply left rotation on parent. Yes or no? There's a small change. In case 2, you can see you are applying left rotation on parent, but in case 3, you are applying right rotation on grandparent, right? So after you do this in case 3, basically, in case 2, you don't change color, but in case 3, what do you do? Before you apply the right rotation, you change the parent color to black and grandparent color to red. Okay, parent here in case 3, parent color that is 7 to black, and grandparent 11 to red. Okay, that you do and then apply the right rotation to grandparent. I hope this is clear. So this is taking left into consideration, right? When the parent of Z, right, is at the left side. But if he's at the right side in the else part, you will find again similar three cases. Okay, this is your insert fix up algorithm. I hope this is clear. Similarly, when you are performing deletion as well, deleting a node over the binary search tree is very similar to that of your binary search tree deletion itself, right? Simple. How when you are deleting a node from the binary search tree, what are the three different possible cases you encounter with? One is the leaf node. If it is a leaf node, simply delete it by making its parent pointer as null. Another case is when you are deleting a node having either left or right subtree, then attach its left or right subtree to its parent position and then delete. That's the second case. And third case is when you are trying to delete a node having both left and right subtrees. What we said, we will find the successor, right? Successor of the root, and then replace that root with the successor and delete that successor, right? That is how exactly the solution we have adopted for what do you call binary search tree. So same kind of operation you're going to apply. That is what exactly mentioned here, right? But then after doing this, you have delete fix up. So again, under delete fix up, you are going to encounter with these different cases. When you find red, okay, when you find red, you need to adjust the colors, and you need to bring back into the red black tree by satisfying the respective five properties that we have mentioned. So that is exactly what here been mentioned with all different possible cases. I hope this you can understand by going through the same. I'm giving this, leaving this for your assignment. Okay, is it clear to all of you?